Set operations with three sets. A Venn diagram with three intersecting sets breaks up the universal set into 8 distinct regions. So we have here the three sets A, B, and C represented by these circles. But these circles break this universal set into actually 8 disjoint subsets. The first disjoint subset that I want to look at is the intersection of all three sets A, B, and C. So that's A and B and C. And then the next one I want to look at is the intersection of only A and B with the exclusion of set C. So that's A and B and not C. Next one is the intersection of B and C excluding anything in A. So that's B and C and not A. And the next one is the intersection of A and C excluding B. So that's A and C and not B, not B. All right, so those are the subsets, the disjoint subsets that are in the overlapping parts. Now we're going to look at the parts that don't have any overlapping with any other sets. So basically the things that are only in A, the things that are only in B, and the things that are only in C. So first, this is the set of things in A and not B and not C. And then we'll have the things that are in not A and B and not C. So that's basically B and not A and not C. And the last one is C and not A and not B. That's the last one in the union, I should say. There's one other subset, actually, one other disjoint subset. The things that are in none of the three sets, A, B, or C. So that's not A and not B and not C. So they're in the universal set, but they're not in any of the overlapping sets, A, B, or C. So let's take a look at an example here. We have a group of 61 employees was required to attend 3 meetings. A total of 42 employees attended meeting 1, 46 employees attended meeting 2, 40 employees attended meeting 3. Of these employees, 32 attended meetings 1 and 2, 29 attended meetings 1 and 3, so 34 attended meetings 2 and 3. 25 employees attended all 3 meetings. So we're going to create a Venn diagram with subsets labeled 1, 2, and 3. And then we're going to label the cardinality of each section of the Venn diagram as indicated by this data. By the cardinality of each section, they're talking about the 8 disjoint subsets. So we have to label the 8 disjoint subsets. The first one we should do, you always want to start in the middle, the intersection of all 3. So it says here that 25 employees attended all 3 meetings. So that means that the number of people that attended 1 and 2 and 3 was 25. I put that in the middle. And then I'm going to work on the pairwise intersections now. So first I'm going to look at those that went to 1 and 2. And it says here that 32 attended meetings 1 and 2, but we have 25 of those 32 already here because these 25 attended 1 and 2 and 3. What we're looking for now is the people that went to 1 and 2 but not 3. So we're going to take 25 that are already here away from the 32 to figure out what goes here. And these are the people, the number of employees that attended 1 and 2 and not 3. It's the total that attended 1 and 2 minus the 25 that attended 1 and 2 and 3. All right, now we're going to do the same thing for sets 1 and 3, or for meeting 1 and 3. And it seems like 29 attended meetings 1 and 3. So 29 should be in this overlap here, in this entire intersection. But there's 25 already here, so I have to take that 25 away from the 29 to get 4 that went to meetings 1 and 3 and not 2. Because these 25 also went to 2. Now I see that the people that went to 1 and 3, that totals 29. 25 plus 4 is 29 in the intersection of 1 and 3. Last pairwise intersection I want to look at is the intersection of 2 and 3. Well, it says that there are 34 people that went to 2 and 3, but 25 of them are already in the set that went to 1 and 2 and 3. So I have to take that 25 away from the 34 that went to 2 and 3, and I'll get the people that only went to 2 and 3 and not 1. So that's the people that went to 2 and 3 and not 1. So there we have 4 of the disjoint subsets. There were 8. We're going to look at the singlets now, the ones that only went to 1, the employees that only went to 2, or the employees that only went to 3, and also the employees that went to none. So for the employees that went to only 1 and not 2 and not 3, well, it says here that 42 employees went to 1. So I just have to take away the 7 that went to 1 and 2, the 25 that went to 1, 2, and 3, and the 4 that went to 1 and 3 away from that 42 to get the people that only went to 1. And that's 6 people only went to meeting 1. I'm going to do the same thing for those that went to meeting 2. It says that 46 employees went to meeting 2. I'm just going to take away these that went to other meetings also. So that's going to be the 46 minus the 7 that went to 1 and 2, the 9 that went to 2 and 3, and the 25 that went to all 3 meetings. That gives me 5 people that only went to 2. And lastly, the people that only went to 3, well, it says that there were 40 people total that went to 3. We just have to take away the people that went to other meetings also to find that 2 people went to only meeting 3. And now lastly, we need to find out how many people went to no meetings at all. We know that 61 employees is the total. There's 61 total employees. So of the 61, only the people in this big union here went to meeting. So I need to figure out how much this total is and subtract it from 61. Well, to find the total, I know how many went to meeting 1 because it says there were 42 employees. So 42 employees went to this meeting. Then I just have to add these 5, 9, and 2 in. So that's what I'm going to do. I'm going to take the 61. I'm going to subtract the 42 that went to meeting 1. Subtract the 5 that went to 2 only. Subtract the 9 that went to 2 and 3. And subtract the 2 that went to only 3. And that leaves 3 people that went to no meetings at all. So there are 3 people that did not attend a single meeting. We're going to use these 61 employees to look at the cardinality of some subset. The first subset I want to look at is this subset here. Find the number of employees that went to meeting 1 and 2 or meeting 1 and 3. So this is symbolically how you'd write that. The cardinality, or the number of employees that went to 1 and 2, that's the intersection of 1 and 2, or 1 and 3. First thing I'm going to do is I'm going to find out how many people went to 1 and 2 because it's in parentheses here. So I'm looking at the intersection of set 1 and 2, which is those 32 people there. If you remember the Venn diagram, there would be 32 people here. 7 and 25 makes 32. We're also going to look at the people that went to 1 and 3. So let's look at the people that went to 1 and 3. There's 29 people that went to 1 and 3. So if I want to bring back in those 7 people in the intersection of 1 and 2, that'll be the union. That'll be the union of those 2 sets. So the union of those 2 sets is represented by these 36 people here. If you add all this up, this is 36. This right here is the intersection of 1 and 2. This right here is the intersection of 1 and 3. So this represents the union of those 2 sets. That's the union. These 36 people is what's represented here. Let's take a look at another one here. We're going to find here now the people that went to, the number of people that went to 1 and 2 or 3. So they definitely went to 1 and they either went to 2 or 3. So that's what we're looking for. We're looking for the people that went to 1 and either 2 or 3. So because the parentheses is around the 2 or 3, that's the first thing I'm going to be looking for, is the number of people that went to meeting 2 or 3. So we just exclude everybody that went to meeting 1. That's these 52 people right here. You can add that all up and make sure it equals 52. Now I want to know the intersection of that with the people that went to meeting 1. So I'm going to find this intersection now. Well, the meeting 1 circle was this circle here. So I just need to take away everybody that's not in the meeting one circle to find this intersection. So I just take away everybody that's not in the meeting one circle, and I get this, which is these. Oh my goodness, it's the same 36 people. It's the same 36 people. That's crazy. Check this out. That means that what I just calculated, the intersection of A and B union C, is equal to, because they had the same Venn diagram, we were talking about the same 36 people, so it's equal to the intersection of A and B union the intersection of A and C. As a matter of fact, I knew from the beginning that they were actually equal, because that's called the distributive property for sets over union and intersection. So basically I'm doing the intersection over a union here, and what this says is I can just do the intersection of A and B and then union that with the intersection of A and C. Just like the distributive property of multiplication over addition. You take the thing out front and you do that operation with both of the things on the inside. That's what it says on the right side here. The distributive property for set union over set intersection. These two equalities right here. There's one more proof I want to look at, and it's the proof of this called De Morgan's law. Basically, De Morgan's law says you can also distribute this negation kind of. So instead of having parentheses with a negation, you can just negate both of the things on the inside and flip the sign over. So instead of an intersection, it becomes a union. And it's the same down here. To get rid of the parentheses, you can just negate both things on the inside and flip the sign over. That's De Morgan's law. Let's see if it's true. So first, we'll look for the intersection of A and B, the inside of the parentheses here. Well, let's see. The intersection of A and B is that part in the middle there. That's the intersection of A and B. And then we need to negate that. So everything but this would look like that. So that's the negation of the intersection. All I need to prove is that the union of not A and not B is this same picture. So let's look at the union of not A and not B. Let's get back to the original Venn diagram. Let's look at not A first. Not A. This is what not A looks like. It's everything outside of A. So it's this half moon part of B. It's this crescent moon part of B. And then let's see. Let's look at the whole thing again and figure out what not B looks like. So not B. What's not B? Well, not B is everything outside of B. It's like the universal set pretty much, and everything in that crescent moon shaped part of A. When we put those together to form a union, so we're going to form a union because remember we have to flip the sign over. The union is just this, that crescent moon and that crescent moon together, which was the exact same shape we had for the negation of the intersection. So it turns out that these things are equal to each other. And that's the first half of De Morgan's law there.